In this video, we're going to talk about the organization and control signaling for a set of RGB LED matrices produced by Adafruit. In particular, we're going to focus on the 16 by 32 LED matrix, but the same ideas apply to larger matrices. And I will note while we're looking at these figures here that from a data standpoint, these matrices are controlled or kind of split into two separate elements: the top half of the array and the bottom half of the array. So in the 16 by 32 array, the top 8 rows have data fed in it or have a single data source, and the bottom 8 rows have a single data source. So looking at the internal organization of this, we're going to focus on one of the two halves. The other half is very similar in its organization and actually has most of the control signals shared. The only control signals that are separate are the red, green, and blue, or RGB control signals. So looking at this diagram here, there are four main elements to the internal structure of this array. The first one is the LEDs themselves. So within a half of the array, we can see that there are a number of rows here. So with 16 total rows, a half of the matrix has 8 rows, which are shown here. And each row has, in this case, 32 LEDs, and it has an enable signal, which is used to turn on the row or not, to enable whether or not the LEDs in that row are going to come on. The second element is what generates these enable signals for the row. So the second element takes in 3 single-bit signals from the outside, the C, B, and A signals, and that determines which of the 8 rows to turn on. And then along with that, there is an output enable signal, which is an active low signal, which determines whether any of the rows are on. So if output enable is low, then that means whatever C, B, and A decodes to, that row will be on. And if output enable is high, then that means all of the rows will be turned off. And this is useful when you're updating rows so that you don't see any flickering or ghosting going on. So that's the second element. The third element is what is used to drive whichever row is activated. So the third element is a set of 32 3-bit latches, and the values stored in these latches are fed to whichever of the rows are currently enabled. To update what is stored in the latches, there is a latch signal that the controller must generate. And when this signal is high, it takes its source comes from the fourth element, which is a set of shift registers. So when we have 32 LEDs and each LED needs 3 control signals, that would lead to a large number of control signals if we were to update them all at once. And so instead we use a shift register, which takes in the 3 bits corresponding to the RG and B values for a single pixel at a time. And we shift in these pixel values over 32 periods, and then we take the values from the shift register and can eventually latch them to be displayed on the LEDs. So in the shift register here, we see that there are essentially 3 shift registers, one for the red, one for the green, and one for the blue pixel information coming in, and this information is latched based off of a clock signal that is fed into this shift register. So this is the hardware organization from a control standpoint. These two figures here show both an abstract representation of how the control signal is necessary to control this matrix, and on the bottom here we have an actual concrete example for controlling a particular row or showing how a particular row is updated. So looking at this control, there is basically 2 pieces to the controlling or signaling to these RGB matrices. The first is feeding data into the shift register. So up here in blue, we've got shown how the clock and RGB signals are fed in to shift in a single pixel of data at a time. So it starts by shifting in the 0th pixel, information for the 0th pixel, and we pulse the clock signal, and then we feed in data for the next pixel and pulse the clock signal, and we do this a total of 32 times. And we can see down on the bottom how we've got, in an extended form, the full 32 clock pulses, as well as the data changing on the RGB signaling that's going in. We feed these data in and we store them in the shift register, and then we often will wait some period of time so what is ever currently in the latches will be able to be displayed on the rows and have enough time to turn on the LEDs and be on for some period of time. After this period of time, we then want to take what we shifted into the shift register and save it into the latches and move on to the next row. So these values that we had previously shifted in are now displayed on the next row. And so the first thing that we want to do when we prepare to do this is to turn off all of the rows in the matrix so that the changes we're making don't lead to any oddities in the output of the display. So to do this, we turn off the display, so we disable the output by turning the signal high there, essentially blanking the display. And then while the display is briefly blank or turned off, we do two things. One, we move to the next row, so we update the C, B, and A values to move to the next row that we want to then display the values we shifted in on. And then once we've done this, we assert our latch signal so that we take the values we shifted in and we take them from the shift registers and we put them into our latches. So to show how this, give an example of this, we're now going to take a look at an example of going through these two different elements, looking at the hardware pieces. So here we've got the different hardware elements. To get started, we're going to assume that we've got some values already populated here. So we're going to assume that C, B, and A are all 0, meaning that we're activating or we're enabling row 0 here. You'll also notice that the output enable signal is 0, meaning that since this is an active low signal, we are enabling that row, so we've enabled row 0. Looking at the latch, you can see we've already got some values in our latch here. So for example, in the 31st pixel position here, we've got a 1, 0, 0 corresponding to red being on and green and blue being off. And up here we can see that this LED is shown as being red. Similarly, in the 30th LED, we see red off and green and blue on, and that corresponds to a cyan color, which we can see up there. So now that we have this, we've got the two different elements of our control to deal with. So the first is to prepare the next set of values we want to display, in this case on row 1. So to do this, we're essentially trying to create this portion of the waveform, and in our example, we're going to have a goal of setting the 0th pixel to yellow, the 1st pixel to white, the 30th pixel to blue, and the 31st pixel to green. And so to do this, since we're shifting into the shift register, the first thing that we're shifting in is the information for that we eventually want on the 0th pixel. And so the 0th pixel we want to be yellow, so we set RG and B to 110 because having red and green be 1 will result in a yellow color for the LED. So we set RGB to 110 and then we pulse the clock. And by doing this, we shift the values into the shift register. And then we look, the next thing that we want to shift in for the first pixel eventually is white, which means we want all of the input bits to be 1. So we set RG and B to 1. We then pulse the clock signal again. This causes those 1 values to shift in and our other values to shift over. And then in the end, we repeat this a total of 32 times. And after we've done this, we would have shifted all of the information in. And you can see, for example, in our 31st set of registers, we've got a value of 0, 1, 0, basically meaning that only the green LED will be on, corresponding to the fact that we only want the green, or we want to display green in the 31st LED. So our shift register is now storing these values. It will continue to store them as so long as we don't pulse the clock anymore. And so now we're going to move on to eventually moving these values into the latch so we can then display them on the next row. And so this brings us to the second element of the control piece, where we want to first turn off the display. So that means setting our output enable to 1. And if you notice, by doing that, we basically disabled set all of our enable signals to 0, which means we're going to turn all of the LEDs off in the matrix. Once we've done that, we then have to do two things. We want to update the row that we're eventually going to turn on. So that means we're going to update C, B, and A to 001 because we're going to move on to row 1. And that corresponds to essentially this transition here. And then the next thing we want to do is latch what we have in our shift register here, and we want to put it into our latches. And so to do that, we need to assert our latch signal, which you can see is what's being shown here. And so we're going to set latch equal to 1, and that'll mean we're going to take the values in our shift register and update them into our latch. So the green that was in our 31st bit position is now over here in our 31st position in our latch. And then now that we've made these updates, we're going to deassert latch so that any additional changes in the shift register don't get brought into the latch in the future until we want them to be. And now that we're done with this, it's time to re-enable our LEDs so that we can turn on our new values. So we're going to put output enable back to 0. And if you'll notice that now, since we're pointing to row 1, our decoder now has enabled the first row. And so we read the values from our latch, and that displays our green, blue, white, and yellow values that we wanted. And so this basically shows how the RGB matrix updates its values. And I will note that as we continue this process, we do it for the remaining 6 rows, and then we go back to the 0th row and repeat this process. And we'd repeat this process continuously and multiple times within a second so that it appears to the user that all of the LEDs are on simultaneously.